Good morning, everyone. Today I'm going to give an introduction of the Earth's gravity field. Let me first ask a question. What is gravity? Gravity is a force, a fundamental force that determines how massive objects interact. In a plain language, we can think of gravity as the invisible force that pulls two masses together. You can see it, you can smell it, you can touch it, but it is there. In fact, it is everywhere. Gravity can explain why does an apple fall from a tree and why can you stand upright on Earth? We all heard of Newton's law of universal gravitation. The live graphic is a cartoon showing that Isaac Newton was sitting under an apple tree and thinking why the apple falls to the ground, and then discovered the law of universal gravitation. The story itself may not be true, but one thing is certain, that Newton is a truly genius. His discovery of the law of universal gravitation must have come from observations of how massive objects interact, such as why apple falls from a tree, and why does Earth circle the sun. While the force of gravity is weak compared to other forces in nature, such as electric and magnetic forces, its effects are the most far-reaching and dramatic. Gravity controls everything from the motion of the ocean tides to the expansion of the entire universe. The magnitude of gravity is closely related to the masses of the two objects. We all know that the moon has much lower gravity compared to Earth. This is a famous photograph of an astronaut taking a giant leap to demonstrate the effect of the moon's lower gravity on a person's weight. On our home planet Earth, we tend to think of the gravitational effect as being the same no matter where we are on Earth's surface. We certainly don't see the variations anywhere near as dramatic as those between the Earth and the Moon. But the truth is, the Earth's gravity varies from place to place because the Earth's topography is highly variable with mountains, valleys, plains, and deep ocean trenches. Here is the equation for gravitational force discovered by Newton. The gravitational force exists between any two masses. So that's why it is called law of universal gravitation. The gravitational force, is proportional, to the masses of the two bodies, and also is a function of the distance between the two, bodies. The capital G is the gravitational constant. So, the gravitational force will decrease as the distance increases dramatically. How does the Earth's gravity field look like? Gravity field is commonly described by gravity anomalies. Gravity anomaly represents the Earth's actual gravity field, differ from the gravity field of a uniform featureless Earth's surface. Here is an example plot of the Earth's gravity field, the GIF 48 model derived from satellite and ground measurements. If you look closely, the gravity anomaly features are closely connected to the topography and the bathymetry of the Earth, the mountain ridges, high plains, and ocean trenches. The gravity anomaly is a relatively small portion of the Earth's gravity field, up to about 10%. Let's take a look at the definition of the Earth's gravity field. The Earth's gravity field is also called geopotential field. The geopotential field is determined by mass distribution within the Earth system and is conveniently expressed in sphere harmonic expansion as the following. So as long as we know the mass distribution in the Earth system, we can determine the geopotential field, at any location in the Earth system. In the equation, r, phi, and lambda are the geocentric latitude, geocentric distance, latitude, and the longitude of the chosen point. Capital G is the gravitational constant, ME is the mass of the Earth, RE is the equatorial radius of the Earth. CLM and the SLM are the sphere harmonics of degree L and the order M. PLM, are the Legendre polynomial of degree L and the order M. The gravity sphere harmonic coefficients CLM and the SLM are related to mass distribution in the Earth system so as we can see, if we know the mass distribution of the Earth system, we can do a global integration to compute gravitational coefficients, the CLM and the SLM. To help us better understand the sphere harmonic expansion, let's first take a look at a simple Fourier transform. Through Fourier transform, a time series, or function depending on time is decomposed into functions depending on frequency. Those frequency-dependent, functions are orthogonal. So in this particular example, the original time series, the red curve is decomposed into the sum of a group of periodic signals. Fourier transform is a powerful tool in digital signal processing. It can help people to understand a time series in the frequency domain. Let's come back to sphere harmonic expansion. That's the same equation we just copied and pasted here. Sphere harmonic expansion is doing something similar, but in the space domain. Fourier transform is commonly done, from time domain to frequency domain, Even though, Fourier transform can also be done in the space domain, so the sphere harmonic expansion is doing a similar, transform. We convert, a field on Earth's surface into different modes. Yeah, for Fourier transform, that's the sine, cosine functions, but in sphere harmonic expansion, that's the sphere harmonic coefficients. So based on the geopotential equation to describe the Earth's gravity field or any gravity field, what we need are simply the sphere harmonic coefficients. Up to a certain degree and order, CLM and the SLM are also called Stokes coefficients. But what are those coefficients? How do we understand those Stokes coefficients? Each sphere harmonic coefficient represents a particular spatial mode of the mass or gravity signal. Here is an illustration of a three-dimensional, sphere harmonic modes for degree 0 up to degree and order 4. So first, let's look at the zonal terms in the middle, column here. The zonal terms are defined as the, order equals to 0. So those terms like, C00, C10, C20, and C30, and C40. Those zonal terms, represent the, mass or gravity change, in a zonal pattern, but just, at different wavelengths. Let's look at the diagonal terms. Those are called sectoral terms. The sectoral terms are defined, when the order equals to degree. So that means for C11, C11, C22, C33, C44, and same as S11, S22, and S33 and S44. Those terms, separate, the Earth's surface into different sectoral, segments. There are some special terms of sphere harmonic coefficients, which have special meanings and special, connections to the Earth system. First, let's look at the lowest degree. That's the zero, degree zero term. The degree zero term represents the total mass of the Earth system, which is a constant and is set to zero by default in terms of, GeoEd anomaly and time variable gravity. The second set of coefficients, are the degree one, coefficients, C11, S11, and C10. Those coefficients represent geocenter motion. Geocenter motion is defined as the variation of the center of mass of the Earth system in the terrestrial reference frame. And C11, S11, and C10, those degree 1 terms are also commonly set to 0 in gravity solutions, as the gravity field is defined in the center of mass reference frame. So this is only an issue related to the reference frame, because we define the gravity field in the center of mass, reference frame. So there's no change of this, particular, origin. The third set of coefficients are the degree 2 terms. The degree 2 order 1 coefficients C21, S21 describe the position of the Earth's figure axis and are related to polar motion. And the degree 2 order 2 coefficients, the C20, describes the flatness of the Earth and affects the Earth rotational rate, the so-called length of day. Even though geocenter terms are commonly set to 0 in the gravity solutions, those terms, actually are needed when using time variable gravity solutions to study mass variation and the redistribution in the Earth system. This is due to the different reference frame used for the two fields. The gravity fields are defined in the geocenter, the center of mass reference frame, and the mass variation are, commonly defined, interpreted in the center of figure reference frame, just due to the different reference frames used. So we need to include C11, S11, and C10 when using time variable gravity solution to quantify surface mass change. The Earth's gravity field can be separated into two parts. The first is the static gravity field, which is time invariant. It's not changing as a function of time. And the second part is time variable gravity field. The static gravity field is mostly controlled by topography and the bathymetry, of the Earth. So you can see for the gravity anomaly, those features are highly correlated with surface topography and bathymetry. And for time variable gravity field, the variations are mostly driven by climate and geodynamic signals. Let's take a further look at the static gravity field. The static gravity field, is normally taken as the average of data over time. This is because the Earth is not static. There are all kinds of mass variations at different time scale, from hourly, seasonal, interannual, decadal to 1,000 or even million years. So how to define and determine the Earth static field is not very simple. So in practice, people will take the average of all data or collected data, from both, in situ historical measurement and from, modern satellite measurement to get a, mean field of the global gravity field, which is often referred to as static gravity field. The definition of time variable gravity field is easy and straightforward. So the observed gravity change is the sum of static gravity field plus the variation part. So the variation part is typically referred to the time variable gravity part. And we can easily convert equation into a different format. So the change of the gravity or time variable gravity equals the observed gravitational field minus the static gravity field. So that's the difference between the observed gravity field and the static gravity field. And the static gravity field is often called the reference gravity field. Let's watch animation of the global gravity field anomaly observed by Grace satellite gravimetry. It's a very short video. This gravity field is purely, from, satellite gravimetry. Without any, other data. In addition to gravity anomaly, GeoID is another important description of the Earth's gravity field. The GeoID is a hypothetical Earth surface that represents the mean sea level in the absence of wind, currents, and most tides. The ocean surface, when there's no dynamic part, no winds, no currents, no waves, no tides, the mean ocean surface, represents the, GeoID. So for the ocean, it's relatively easier. As long as we can get rid of, the dynamical part, we can, treat the ocean surface as the GeoID. For land part, is relatively tricky, but we can still compute the GeoID, location. So for the GeoID height, that's the definition. Here is the definition. So the GeoID height is the, the height of the GeoID or the location of the GeoID with respect to the reference ellipsoid. The ellipsoid represents the mean uniform, shape of the Earth. The Earth is not really a sphere because, the rotation of the Earth and is kind of flattening, even though the flatness is very, very small. But, in geodesy, we use the ellipsoid to represent the mean uniform surface of the Earth. So what does GeoID height look like? The left-hand side is Earth's topography with mountain ranges up to several thousand, several kilometers above the sea level, and also ocean, trenches up to a few, kilometer under the sea level. The Earth shape, looks like a sphere, as I just mentioned, but it's actually an ellipsoid. This is mainly because the Earth rotation, the status. However, the Earth's flattening is very small. The difference between the two radius, one is the axial, radius, and the other is the equatorial radius. It's very small. They only differ by 1 part over about 300. And the right-hand side is the Earth GeoID map derived from the EGM 2008 gravity field model. So clearly, the GeoID surface is not a sphere and not even an ellipsoid. It's more like a potato. This is mainly controlled by the Earth structure, the surface topography, and also the interior density structure. But don't be fooled by the illustration itself. Just look at the color scale. The geoid shape. This illustration is exaggerated. The actual variation of the geoid height is pretty small. The magnitudes are up to negative to positive, meters. If you compare to the topography, there's up to 10 kilometers. So the geoid anomaly, not geoid anomaly, geoid height, spatial variability actually is very small. Now let's look at the time variable gravity field. There are three representations of time variable gravity field. The first is sphere harmonic coefficients. As we know from the definition, those are the fundamental variables to describe the Earth's gravity. As long as we can determine the variation, the temporal variation of those coefficients with respect to a reference model, we can determine the time variable part of the gravity. So those are the typical products provided by satellite measurements, the variation of those coefficients. We can also use the time variable gravity field to infer mass variation, mainly on the Earth's surface, because surface mass flow change. And another representation of the time variable gravity field is the geoid height change. So the top equation, gives the relationship, between surface mass density at any location and the observed variation of gravity coefficients, gravity sphere harmonic coefficients, CLM and SLM. In this equation, in addition to some other constants such as the equatorial region of the Earth, there are two other constant. One is the mean density of the Earth, rho AVE, and the other is the love number. The KL is the love number of degree L. And similarly, the bottom equation gives the relationship between geoid height change and the observed gravitational coefficients, the Stowe coefficients. So in general, mass variation and geoid height change are two commonly used representations of time variable gravity field. Here is an example, from GRACE satellite gravity measurement. We are going to talk a little bit about GRACE later. So based on satellite observation, we can determine the time variable gravity field and use those solutions to study, surface mass variation. Here we give two examples. One is for April 2014. The other is for October 2014. Basically, just pick up, two, month as an example to show the spatial variation and also the seasonal variability. You look at the seasonal variation, at different locations in the world, the Amazon and other places, and also some very significant, climate-driven signals like ice melting over Greenland and also ice melting over West Antarctic. Now let's look at another important issue, how to understand the spatial resolution of gravity field. This is a very important, question, for many genetic and geophysical applications. Spatial resolution is a very critical, parameter. So we want to understand, the spatial resolution of a gravity field model. We use the GU8 height change equation, as an example. So each sphere harmonic, coefficients represent a particular spatial pattern of different wavelengths. Degree L, coefficients cuts the Earth's surface into 2 times L segments. We use the sectoral, modes example here. So you can just look at this, plots we already showed earlier. Yes, think about the different, sphere harmonics and their relationship to the wavelength, of surface mass or gravity change. So the degree 1 term cuts Earth's surface into 2 halves, and the degree 2 cuts Earth's surface into 4 halves, 4 parts. And the degree 3, cuts the Earth's surface into 6 parts, and the degree 4 into 8 parts, etc. So let's do a simple math. The circumference of the Earth, is about 40,000 kilometers. We can easily do the math. That's a 2 pi r. If we given the mean readings at the equator, we can easily compute the circumference of the Earth. That's just about 40,000 kilometers. So the corresponding spatial resolution of a given degree L sphere harmonic is about 20,000 kilometers divided by L. Just because, the 40,000 kilometers are divided by 2L, so that's equivalent to 20,000 kilometers divided by L. So to understand the spatial resolution of the gravity field, basically, it was determined by the highest available degree and order sphere harmonics. So ideally, we hope to get the sphere harmonic coefficients up to infinity degree and order. So we can get very high, spatial resolution. The higher degree of the coefficients, the higher spatial resolution, as we showed earlier. However, in the real world, only limited degree and orders of sphere harmonics will be available. So a truncation at a given maximum degree and order, for example, L, capital L, is unavoidable. With truncation at degree 60, I just list 3 examples here. So with truncation at degree 60, the highest spatial resolution we can reach is about 330 kilometers. With truncation at degree and order 120, the spatial resolution, the highest spatial resolution we can reach is about 167 kilometers. And with truncation at degree and order 180, the highest spatial resolution we can reach is about 111 kilometers. These are the true spatial resolution by definition. We assume there's no noise or error in the observed gravity sphere harmonic coefficient. If there are certain noise and the error in those coefficients, we need to do some kind of averaging or smoothing. Then the smoothing itself will also degrade, the spatial resolution of a given, gravity field. So we just talk about the ideal case. There's no noise, no error in the observed gravity sphere harmonic coefficients. So that's, the best we can get, for a given degree and order, at 180 1 degree on the Earth's surface, 1 by 1 degree on the Earth's surface. That's the highest spatial resolution we can get. In the case for Grace, it's truncated at degree 60, even without any spatial filtering, 330 kilometer or 3 by 3 equal area degree Grace. That's the highest spatial resolution we can get. Now we look for another issue, how to measure the gravity and gravity change. We know gravity and the gravity variation are important genetic variables, but how can we measure gravity and the gravity change? On the left-hand side, there are two pictures of the traditional and the absolute gravimeters. And on the right-hand side is a picture of the superconducting gravimeter. The absolute gravimeters provide absolute measurements that are suitable for monitoring long-term change in gravity due to either uplift or secular mass movement. Those instruments are normally moved from place to place to make repeated measurements, often over many years. The superconducting gravimeters provides continuous high precision gravity measurements at observatory locations. They are suitable for studying tides, seismic modes from large earthquakes, and atmospheric and hydrological mass loads. The superconducting gravimeter is large and also heavy due to the liquid helium cooling system, and it's not suitable for field measurement. That's why we always put the superconducting gravimeter in certain laboratories, stations in a fixed location. Here is a map showing the global distribution of superconducting gravimeter stations. There are only about 30 stations in the world, mostly in the northern hemisphere. These stations are important for local measurements and studies, but are certainly not enough for measuring global gravity field. Now let's look at the major challenges of measuring the global gravity field. Here are some pictures of people carrying portable gravimeter to the field to take measurements. There are no practical way to survey the global gravity field using this type of gravimeters. Just consider the enormous scope of the world, and 2/3 of the world surface are covered by oceans. It is even more challenging to measure variations of the gravity field as a function of time, the temporal variation of the gravity field. Both absolute and the superconducting gravimeter are important measurements, are point measurements, and there are only a few dozen of superconducting gravimeters available, over the world, mostly in the northern hemisphere. So relying on those in situ data are simply not enough. Another option is to use, airborne and shipborne gravimeter gravity measurements. People can use airplanes and ships to carry gravimeters to different locations to measure the gravity field. Those historically accumulated gravity observations are important and have been used to determine the static gravity field. But those data are far from adequate to give us a clear and accurate picture of the world gravity field, especially over the ocean. So in terms of measuring the global gravity field, especially over the ocean, the use of ground-based techniques is very limited. People have to seek help from the space. Since early 90s, the advancement of satellite altimetry has brought a completely new era of measuring the Earth's gravity over the ocean. Satellite altimetry is regarded as a revolutionary space geodetic technique. This graphic illustrates, how satellite altimetry works. While flying in the orbit, the satellite altimeter sends down a microwave signal to the Earth's surface and measures the returning signal reflected from the sea surface. Using the traveling time of the signal in the satellite altimetry, a satellite altimeter can determine the height of the sea surface with respect to the satellite orbit. Through some further, calibrations, scientists can determine the sea surface height change with respect to the reference ellipsoid. So using satellite altimetry, we can determine the variation of the sea surface height very accurately. Altimeter observed sea surface height change represents the sum of two parts, the geoid height plus dynamic ocean topography. The dynamic ocean topography is controlled by the ocean dynamics, the circulation waves, wind-driven, variations. After removing dynamic ocean topography from altimeter observed sea surface height change, satellite altimeter can help refine geoid over the ocean, can help improve the quantification and determination of geoid and the gravity anomaly over the ocean. Here is the cluster of satellite altimeter missions sponsored by US NASA and European Space Agency ESA over the past few decades. It starts with the Topax Poseidon mission that was in operation over the period between 2002 and 1992 and 2006. The Topax was the first successful satellite altimeter mission, was designed for only 5 years and ended up flying in orbit for over 14 years. That's an amazing achievement. And the Topax Poseidon follow-on mission, Jason-1, was launched in 2001 and decommissioned in 2013, also flying in orbit for about 12 years. And Jason-2, which is also a follow-on mission of the Topax Poseidon. The Jason-2 was put into orbit in 2008 and stopped operation in 2019 with another about 12 years observation. And the latest one was, Jason-3 was put into orbit in 2016, early 2016, and is still in operation. There are a few other altimeter missions that will be, launched in next few or several years. Among them, the Sentinel-6 was originally scheduled to be launched last year, sometime 2020, but was delayed to later part of 2011. Now let's look at an amazing map, the global marine gravity anomaly map derived from satellite altimetry. So it's hard to imagine without satellite altimetry measurement, how can people capture all the detailed structures, detailed features of the Earth's gravity field. Those are closely related to the seafloor bathymetry. So satellite altimetry has been a very successful technique, not only in monitoring the global sea level change, the climate change impact on the global sea level, but also on quantification or improving the marine gravity field, especially the small feature, the high resolution and small features of the world ocean. The last part is also about space, observations, the satellite gravimetry. We can measure the Earth's gravity field from space using satellite gravimetry. We have to, talk about, the GRACE. We already mentioned it a few times. GRACE stands for, GRACE is a twin satellite mission, jointly sponsored by US NASA and German Space, Center. GRACE stands for Gravity Recovery and Climate Experiment. Utilizing a revolutionary, inter-satellite tracking technique, GRACE, is the first dedicated satellite gravity mission to measure the Earth's gravity field and its temporal variability. GRACE was launched in March 2002 and decommissioned in November 2017. Similar to the TRIPAX altimeter mission, GRACE was designed for only 5 years, and it actually fly in the space for over 15 years after being decommissioned in 2017. As its name shows, the two major objectives of the GRACE missions are first, gravity recovery, second, climate experiment. So the gravity recovery means the primary goal of GRACE is to measure the Earth's gravity field, not just the static field and also the time variable field. Actually, the time variable part is even more important or is more significant contribution from GRACE. And the second objective is to study the world climate, because the time variable gravity field is mainly driven by climate signals, plus some solid Earth geophysical signals. So we can use, GRACE time variable gravity field to study mass variation in the climate system. GRACE is regarded as one of the most successful, Earth science missions in human history. The GRACE follow-on, mission was launched, on May 22nd, and to continue the legacy of GRACE. GRACE follow-on is basically a copy of GRACE with a newer generation of hardware. Now let's watch a short video of the launch of the GRACE follow-on mission. I will explain how GRACE and the GRACE follow-on satellite altimetry works.
9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of GRACE follow-on, continuing the legacy of the GRACE mission of tracking the movement of water across our planet.
Vehicles pitching downrange.
Even though I'm a member of the GRACE Science team, unfortunately, I was not able to watch the launch of the GRACE follow-on mission on site. We were able to sit in our conference room to watch the real-time, broadcast of the launch. This was an amazing experience. After the launch, the two GRIS satellites were adjusting their orientation and orbits. The two satellites are mostly the same. Basically, we can say identical with slightly difference. Now, after adjusting the orientation and orbit, the two satellites will fly in exactly the same orbit, about 500 kilometers above the Earth's surface, one following another with an inter-satellite distance of about 220 kilometers. The two GRIS follow-on satellites are equipped with a K-band ranging system to measure the distance between the two satellites with very high accuracy. And the GRIS follow-on system, is also equipped with a laser ranging system. The laser ranging is defined for the next generation of GRIS satellites, just for experiment. While flying in orbit, so any changes of mass in the Earth system, like spatial variation from mountain range, temporal variation due to glacial melting, will all affect Earth's gravity field, and in turn to cause variations of the inter-satellite distance. The K-band ranging system can measure the tiny change of the inter-satellite distance with very high accuracy. That information can be used to derive changes of the gravity field. This is the really amazing part of the GRIS and the GRIS follow-on mission. So we can use the change between the two satellites to infer time variable gravity variations. So what we can get from GRIS, this is a map we already shown earlier. So the global gravity anomaly from GRIS and other data. So we can combine GRIS observed gravity solutions with historically collected data from either ground or shape or airplanes to derive a better gravity solution. This model is called a GRIS intermediate field fold-8 model, which is an improved mean static gravity field model that combines GRIS with terrestrial and ocean gravity information for the small scale features that GRIS alone cannot resolve. Here is another example of using GRIS observed time variable gravity field to monitor the March 2009 severe flooding event in the Amazon basin. We only show 6 monthly solutions in the Amazon basin. You can easily tell the migration or the evolution of the flooding water in the lower center and the lower Amazon basin from 2008, September 2008, November 2008, January 2009, March 2009 until July 2009, and the flooding event, the water storage, surface water storage, the change reaches the maximum in March 2009. So satellite altimeter is an amazing tool for help people to better understand the climate system. So what else can GRIS do? What can GRIS really do? This is a global map, of mass change rate derived from GRIS. Let's take a closer look. There are many interesting, amazing, climate-related and geophysical-related features on this map. First, is the Greenland ice melting. They're very significant ice melting over the Greenland during the grace period. And the second is a positive anomaly that's due to the global isostatic adjustment, the so-called GIA effect. That's a solid Earth geophysical signal. It's the rebounding of the Earth's surface, due to its viscoelastic, effect. And the next is the Alaskan, mountain glacier. Also the significant, ice melting, in the Alaska mountain glaciers. And next is the U.S. Midwest drought and the U.S. Central Valley groundwater depletion in U.S. California. And another mountain glaciers, the Patagonian ice field in South America. And another very significant, ice melting in West Antarctic and the Antarctic Peninsula. Two, ice melting regions in East Antarctic. This is very significant, because for East Antarctic, people normally believe it's so cold for the ice sheet to melt. You can only imagine accumulation, but not melting. But due to global warming in certain locations, over East Antarctic, we start seeing, ice melting, in some locations. And here, there's the East Antarctic snow accumulation. Another interesting feature, that's the sand-based basin precipitation increase. That's in South Africa. That's another very interesting solid Earth geophysical feature. That's the 2004 Sumatra earthquake deformation. Greece can capture the seafloor deformation due to large earthquakes. That's the Caspian Sea level drop. Caspian Sea is actually a lake, the largest lake, inland water body, and largest lake, in the world. Over the past few decades, Caspian sea level is, decreasing dramatically, causing very large, huge, environmental impact to the Caspian region. There's another interesting, hydrological signal, the Northwest Indian groundwater depletion observed by Grace. And another solid Earth geophysical signal, the Scandinavia glacial isostatic adjustment. And the last one is 2011, the Japan earthquake, the seafloor deformation. So Grace can really do a lot of things, With the launch of Grace and Grace follow on, we have a better view of the Earth's climate system. So Grace is counted as one of the most successful Earth science missions in human history. Now let's come to a summary. Let's just give a summary of what we have talked about today. First, we talk about what is gravity. Gravity is a force. It's a force, pull two masses together. We talk about sphere harmonic expansion of the gravity field. That's the convenient way to express the gravity field using sphere harmonic expansion, not just the gravity field. Any two-dimensional field in a sphere system, coordinate system, can be represented by sphere harmonic expansion. We talk about some special terms of the gravity sphere harmonic coefficients. The degree zero term represents the total mass of the Earth system, and degree one term represents geocenter variation, and degree two terms and their connection with Earth rotation. We talk about static gravity field and time variable gravity field. We also discuss three, representations of time variable gravity field: the sphere harmonic, representation, GOA height change, and surface mass variation. We also introduce, how we can measure the Earth's gravity field, the in situ observations from traditional, absolute, and the superconducting gravimeters. And we talk about satellite altimetry, using satellite altimetry to measure the sea surface variation and the marine gravity anomaly. We also, talk about GRACE and GRACE follow-on satellite altimetry, satellite gravimetry, technique. Um, Along the way, we mention the limitation and advantages of the different observational techniques. I think that's all for today. Thank you for your attention. And we are going to talk about some other topics next time. Okay, thank you. See you next time.